Hello everyone. In this video, I'm going to derive the expression for displacement in the case of a single degrees of freedom damped free vibration. So the title is a bit complicated, but anyway, as we progress, as you continue to watch this lecture, I think the concepts will be demystified and I will try my best to explain the concepts as explicitly as possible. So to begin with, let me draw a spring mass system. So here we go. You can see that I am putting a spring there. And I'm also putting a damper. So there is a mass that is going to oscillate. That is M. Okay, let me define the properties of the system. There is a spring, so definitely I have to define something called a stiffness. K. You all know what is stiffness. It is the amount of force that is required to stretch a spring by 1 unit length. So it's force divided by displacement, x. So that is stiffness. Okay. For example, if the value of stiffness is 1000 Newton per mm, then you have to put 1000 Newton force to stretch or compress the spring by 1 mm. Okay. And I have also put a damper here. So what is the role this damper is going to play? This damper is going to play the role of friction, which means that over the period of time, it's actually going to dissipate whatever energy that you are going to impart in the system. Then it's actually going to dissipate that energy. So the vibration is not actually going to go forever. The vibration will actually die down over the period of time. So how it is going to die down, whether it is going to oscillate and die down, or whether it is going to die down exponentially, whether there is going to be exponentially decaying solution, all this we will see. It depends on the properties of the mass, the spring, the stiffness, okay, the natural frequency. Okay, to begin with, let me first establish the physical scenario a little bit more clearly. What I'm actually going to do is I'm going to stretch the spring. So look for green color, everyone. I'm going to stretch the spring by pulling this mass over here. So this is the new position of the mass. Maybe I can represent the new position of the mass by dashed lines here. So there you go. That is the new position of the mass. That is our mass M. So this is the stretched position. So the displacement of the mass is x. Suppose if this is the maximum displacement, you can, sometimes I will be using the notation capital A that stands for the maximum displacement, which means maximum amplitude of displacement. So I may use the notation capital A for maximum amplitude. Okay, now x is the displacement, and of course the moment I leave the mass, the displacement is going to change with respect to time. So I have to say the displacement is clearly a function of time. So when you are stretching this mass to this particular distance, the new position, just exercise it in your imagination. It is more an exercise for the imagination than the intellect. The moment you leave the mass, you know what's going to happen? The mass is going to bounce back to its previous position. But when it bounces back to its previous position, it's going to overshoot this position and it's going to go over here. So the reason why the mass goes back to the previous position, you know intuitively that because when you're stretching the spring, it is the spring that is going to pull the mass back to its equilibrium position. Okay. So I'm going to write the action force that actually pulls the mass back to its equilibrium position. So here we go. Let me write the expression for the action force, the force that actually pulls the mass back to its equilibrium position. That is the action force, and that is the spring that is pulling the mass. So right from here, you can see the spring force that is pulling the mass back to its equilibrium position can be given by the expression K into X. So it is this force, is the action force that is going to pull the mass back to its equilibrium position. Okay, so it is K into X. That is action. And according to Newton, for every action, there is going to be an equal and opposite reaction. So what do you think the reaction force is going to be? So here we go. The reaction force is going to be the inertia force, because when you are pulling this mass, right, this mass is going to offer a reaction, and that is given by Newton's second law. F is equal to ma. So that is going to be one reaction force that is going to come. And also the damper is going to offer a reaction, right? Now first let me explain how this force is going to come in the first place. This F is equal to ma. Just imagine you are in deep space, far from any gravitating objects. This is just an example. And suppose you have a string, maybe a string, and you have a mass m. And if you are pulling this mass in this direction to the left hand side, right, then what is actually going to happen is, if you are pulling this mass so that the mass is going to accelerate with an acceleration a, then you will be experiencing a force in the opposite direction, in this direction, and that force will be equal to ma, mass times acceleration. The same is true when you push the mass. When you push the mass, then you are actually going to experience a force opposite to the direction of the push. And that is the reason why when astronauts, when they go out of the space capsule, they have to use a cable, right? They actually tie it around their waist, and that cable is connected to the space capsule so that they are not going to fly off deep into space. If they are giving a push to the space capsule, then according to Newton's third law, they should be experiencing a force in the opposite direction. They will be moving apart from the space capsule. They will be moving away from the space capsule. Okay, fine. I hope you're able to understand the concept. And I told you that there is one more force, reaction, that is going to come, and that reaction will come from the damper here. So this damper is going to offer a reaction, and obviously just imagine that greater the velocity, greater is going to be the resisting force, right? It's quite obvious. Suppose you are moving your table, then the friction force is going to be greater when the table is moving with your greater and greater velocity. If you are just trying to push the table, then of course greater the velocity of the table. This is just an analogy, right? Just an analogy. Maybe if you are moving against air, then with the greater velocity, if you are moving against air, then you are going to experience a greater drag force. In exactly the same manner, you are going to experience a greater force that is directly proportional to the velocity. Okay, so there is a force that is directly proportional to the velocity of the system, that is dx by dt, because velocity is change in displacement with respect to time. And if you want to remove a proportionality, you have to introduce a proportionality constant, and that proportionality constant is c, right? This is the proportionality constant. Now you can define something called as, you can define c, which is the proportionality constant, and they have a name for this proportionality constant. It is called as the damping coefficient. Okay, it is called the damping coefficient. Simply, it is the proportionality constant, but you can define the proportionality constant in a minute. So if you look very carefully, this is the force that is offered by the damper. So you can call that as the damping force. Okay, so we can call this as the damping force. So clearly the damping force, here I am writing that expression, damping force is equal to damping coefficient into velocity. So you can define something called as the damping coefficient. Damping coefficient is damping force. It is the ratio of the damping force to the velocity of the mass. There we have defined the damping coefficient. Maybe it's pragmatic, right? So let us recapitulate the concepts that we have discussed so far. You have a spring mass system. Of course, there is a damper. The role of the damper is it's going to dissipate the energy. So the vibration is not going to go forever. It's going to dissipate the energy and the vibration will die down. So when you are stretching the mass to a new position, x of x, then the moment you leave the mass is going to go back and it's going to overshoot the equilibrium position here. So when the mass is going back to its equilibrium position, The force that is actually pulling the mass back to its equilibrium position is going to be the spring force, which is kx. And of course, there is going to be an inertia force that is offered by the mass, which is a reaction. And there is also going to be a reaction that comes from the damper. So that is directly proportional to the velocity. And if you want to remove the proportionality sign, you introduce a constant, and that constant is damping coefficient. You can define damping coefficient. Now wait a minute. According to Newton's third law, action should be equal to reaction. Well, we can equate that. But watch it very carefully. This is very important at this point of time. The moment the mass crosses its equilibrium position, then keep it in mind. It is the spring force that is going to offer the reaction. And it is the momentum of the mass that is going to be the action. So there is a role reversal that is going to take place the moment the mass crosses its equilibrium position. The spring is not going to pull the mass. The spring is going to offer resistance to the movement of the mass. So maybe you may want to play back this particular sentence and allow the concept to sink naturally inside of you. So the moment the mass crosses its equilibrium position, it is the spring that will offer the resistance. So it's not going to be the spring that is going to pull the mass. What is making the mass continue to move in this direction is actually towards the left hand side, is actually the momentum of the mass. Okay, so that the rate of change of momentum, that becomes action, and the resistance will be offered by the spring. So that concept I can explain. So now at this point of time, if you just equate the action and the reaction by using Newton's third law, then we are going to get this expression. So action is given by kx, and the reaction is mass times acceleration. Acceleration is change in velocity with respect to time, and velocity is change in displacement with respect to time. So you get m into d squared x by dt square plus, and there is a damping force, c into dx over dt. And obviously, the two forces are going to be opposite in nature, so please put a negative sign here. If you just rearrange this equation, throw the right hand side towards the left hand side, the equation that you are actually going to get is m into d square x over dt square plus c into dx over dt plus k into x is equal to 0. Let me put a box, and I'm going to call this as GDE, where GDE stands for the governing differential equation. I've already told in many videos that if you have a differential equation, there is always a secret that is stashed inside the differential equation. There is always a secret that is hidden inside the differential equation. And your objective as engineers, your objective as did I say physicians? I'm sorry. Your objective as physicists, maybe physicians also in future. And your objective as a mathematician is to take the secret out. And in our case, that secret is this x, dependent variable. That is the secret. So this is our secret. If you can solve this differential equation in a very, very methodical and systematic manner, you can get the secret out, which is x. And what is x? It is the displacement of the mass, and it is a function of time. You can tell how the mass would evolve, how the displacement would evolve with respect to time, which is a great thing that enables you to take some insightful and actionable engineering decision. Let us see how we can do that. Yeah.